a little bit about the background, and then freight is an important part of our daily life. And then in the United States, freight transportation is continued to be anticipated to grow. And then in the next 20 years, we anticipate the freight traffic is going to continue to grow by another 50%. And this is actually, interestingly, in the past year or so, the unexpected pandemic of COVID, and also the growth of e-commerce, actually further highlighted the importance of freight transportation, and then particularly the change related to the home deliveries has been really changing the landscape of freight distribution in urban and rural settings. And we all know that actually freight is important, not only because it's related to our daily life, but it's because freight transportation has a lot of externalities. It does contribute to the congestion that we experience every day. It has safety implications as well. We see mixed traffic between trucks and other private vehicles. And particularly freight has a significant impact on infrastructure. And this is something that actually is very distinct as compared to other types of transportation or traffic, where freight vehicles are generally heavy, and then they have a huge impact on infrastructure. And then the sort of the sustainability and durability of our infrastructure systems highly depend on freight transportation. And of course, freight transportation is a major emitter for pollutants, and actually makes the most noises in transportation. So with all this, we want to have the better freight systems in our lives. And particularly, just to sort of put things into context, we look at planning freight distribution networks. And then generally, freight transportation system is to serve the purpose of actually meeting supply and the demand. Essentially, we try to bridge the gap in between over time and over space. So this involves actually very often several layers of transportation. One layer has to do with essentially the line haul part. Those of you who are familiar with logistics and the freight planning would understand that actually very often it's efficient to have a hierarchical system for freight distribution, where we use bigger vehicles or larger vehicles and more efficient modes to do the line haul part with long distance travel. And then this will actually reduce the cost on average for overcoming long distance. And then when we get closer to the customers, and very often we do transshipment, and then we very often do local delivery, the so-called last mile. And the last mile, often we would like to have flexibility in the delivery, such that actually we could serve the passengers better. So very often the design or planning of a freight distribution network is about the trade-off between the line haul part, the long distance, large volume, low cost mode, versus the last mile. The last mile is higher cost, but requires more flexibility. So this is essentially the sort of the fundamental trade-off we have in the freight distribution network. But then the emerging revolutions and technologies that we often have been seeing. There are a lot of technological advancements in recent years. And then the freight industry is actually being revolutionized in a sense. Actually, we have technologies, for example, very much related to our CCAT consortium here, is that we have autonomous vehicles being tested and then being deployed in the field now. And then this particularly leads to revolution to the freight industry, particularly regarding autonomous trucks. And then many companies are currently testing these technologies. And then autonomous trucks actually, as we will see in a moment, have significant impacts on the freight industry regarding the efficiency, regarding the sustainability, regarding the cost, and so on. So everything. So this is actually one part of the system that we want to discuss about here. Essentially, how this emerging autonomous trucking technologies would have an impact on the line haul part of the freight distribution network, and how we are going to be able to design the freight distribution sort of line haul part under the consideration of platoon transportation. Then another part of the sort of technology that's really having a direct impact, and then a lot of the companies are testing, is the commercial UAVs, or otherwise called drones. And then using drones for commercial business, and then essentially drones provides another way of delivering freight to the customers, and then sort of overcoming the last mile flexibility requirements, so essentially. And then particularly in urban settings, when we have a lot of congestion on the surface streets, drones provide another way. And then particularly also in rural areas, when actually using huge vehicles to travel around to provide the last mile delivery is costly and inefficient, then drones provides a very nice alternative. And actually these two sort of technologies go hand in hand. They are not separate. There actually has been a lot of work ongoing currently regarding how we actually use trucks, autonomous trucks, to do the line haul part, and together, try to redesign the whole platoon and then the distribution network, such that we accommodate the emergence of the drone delivery for the last mile. So this actually can be planned simultaneously. So this is sort of the major focus of our discussion today. So just a little bit about today, what we're going to do in the next maybe half an hour. We will be talking a little bit about the line haul part, how the research team here at UIUC here has been working with everybody else to try to improve the line haul shipments of our truck platooning. And then I will start by briefly having an overview about the benefit and the cost of truck platooning. This is some work that we have been working on for a couple of years. Some of the sort of building blocks has already been covered last year in this conference, but hopefully that's just setting the foundation. So we will understand the benefit and cost of truck platooning, and then some of the recent work we have done is regarding how we plan the network of truck platoon lanes. So essentially dedicated lanes for truck platooning, sort of a network design model. And then in order to do that, we need to understand the generalized link cost function. So essentially putting all the costs associated with platooning together into a unified framework, and then use that as a building block to do the network design. So this is some of the work we have done recently. And also simultaneously, we have been doing some work about the last mile, the UAVs, and essentially the benefit and cost, and some of the models we have been building, and particularly the energy analysis that we have been doing. So this is sort of the outline of today's work. So if I may, next, I will briefly review some of the earlier work that has been done by myself and also my colleagues here at Illinois regarding the benefit and the costs of truck platooning. So truck actually is important, particularly in the United States, and I think worldwide. It has significant impacts. I mentioned about the externalities of freight, but when truck is sort of in the picture, we understand in the United States, for example, truck is carrying a big percentage of the truck, sort of the freight in terms of tonnage, and also that the truck is not particularly efficient, unfortunately, regarding energy consumption. So essentially, all that I'm trying to say here is actually the truck is actually a big sort of a consumer of energy, and it's important for the freight industry here in the United States and worldwide. And actually, also another point I want to mention here is actually for trucks. Those of you who have taken Transportation 101 would remember that actually for truck fuel consumption, there are several major components in sort of the resistance, and I want to mention that actually one of the biggest component, more than 50% of trucks fuel is actually used to overcome aerodynamic drag, especially for trucks that are traveling at a higher speed. The air drag is increasing as at least the quadratic function of the speed, right? So this is actually some of the background. Traffic normally has a huge impact on energy consumption as a whole. And also another thing particularly interesting about trucks is that trucks has a huge amount of impact on the pavement infrastructure. This is actually very different from the passenger transportation that normally we talk about passenger cars. But then truck traffic in the United States forms about 11% of the traffic volume, but actually causes over 99% of the roadway wear and tear. This is actually quite interesting because, again, someone who had taken pavement 101 would actually know that actually truck, the damage of axle loads to the road increases as a horsepower of the load value. So essentially a 10-ton truck is actually 160,000 times more damaging than a passenger car. So it's like this is just actually blowing out of proportion. So the trucks is actually the dominating factor for roadway deterioration. So and then, as you can imagine, as our freight continues to increase, one of the big impact is about the infrastructure damage. And then a lot of the we started looking at this problem many years ago, actually at a conference where the local agencies in O'Hare, near O'Hare, near their intermodal terminals, actually complain about how quickly their payments gets damaged by all the truck traffic near the railroad yards. It's just every 2-3 years they have to repave the roads because it just get damaged so quickly. So as I hope this slide shows you the two major factors we're going to be considering here. One is regarding energy consumption related to truck traffic. Another one related to the infrastructure damage the truck traffic is imposing on our society. So a little bit about the revolution that we're facing here. So we all understand all these impacts and so on from the truck traffic, but now the autonomous and the connected traffic is essentially reshaping the landscape, and then particularly in the line haul part, the truck platooning is becoming one of the opportunity for us to improve our performance, and then actually opportunity and also maybe potentially a curse. So we will talk about that in a moment. But then essentially truck platooning, I guess everybody knows very well what it meant. It's essentially the truck traffic vehicles actually tend to get together almost with the help of information technology and autonomy. The trucks can actually get closer to each other in very sort of a close spacing and a temporal gap or clearance, if you want to call it. Then actually they travel together almost like a train. And then the benefit of this, actually, obviously, first of all, we can do it, right? We can now have the capability of putting trucks together and in very close range, very compact convoy, and then they can travel at a higher speed. So without the human intervention or human error, then essentially traffic actually gets improved in some sense. As you can imagine, the vehicles travel still at a very high speed, even if the density is high. This actually defies the traditional fundamental diagram that we would normally anticipate people slow down when they see a lot of traffic around them. So this is one potential improvement that we see, and also there's safety implications from that. But particularly another benefit from truck platooning particularly is actually the potential of lowering fuel consumption and emissions. This is essentially something due to the aerodynamics drags. As aerodynamics is actually, when we have the vehicles actually forming almost like a compact train actually on the freeway, then essentially the air drag gets reduced. So this is actually some of the earlier work we did almost 2 years ago regarding how we can actually understand the impact of a truck forming a platoon, and actually how we build how actually essentially the energy consumption is going to be dependent on the spatial gap in between the vehicles. And so essentially our spacing, I should say, in between the vehicles, and also the potential lateral displacement. So essentially the vehicle, if they form a perfect convoy with perfect alignment, then essentially there's certain sort of air drag. But then if there's actually potentially some displacement laterally, like there's a little distancing here, then what is actually the air drag, and then how the air drag is going to change as according to the location of the vehicle in the platoon, and so on and so forth. So we build the finite element models to try to understand air drags, sort of a free dynamics modeling here. So this is earlier work. We did this 2 years ago, and then we were able to put things together to understand, for any, I hope I have some animation, but maybe it's getting slow. Okay, essentially we try to understand under any arrangement of trucks in a platoon, then how is going to be the air drag dependent on the organization, or we call configuration of the platoons. Essentially, how much this spatial gap we have here, and how much lateral displacements we have there, and how large the platoon is going to be, how many vehicles we put it in one platoon. Okay, so this is one part of the analysis we did. This is a review of earlier work, and then so essentially we found out actually also from the literature and also from our own research that there is a significant amount of fuel saving opportunities from truck platooning, and then this is actually great because as we said, the air drag actually is more than 50% of the fuel consumption of trucks, and then trucks are a big consumer of energy in industry. But then there's no free lunch. I think the platooning actually has advantage of energy saving, but actually it does have damage to the payments. As you can imagine, the damage accumulation depends on the loading frequency and then loading sort of concentration. So this is a picture to show something that we may expect in the future, especially when the platooning is really widely accepted. If we are not careful, then actually the payments gets damaged very quickly. This shows very significant rotting actually along the wheel paths of trucks. So our colleagues in payments have already been doing a lot of work in the past 2 years to try to understand the impact of a truck sort of a loading pattern onto the payment, and particularly in light of the autonomous trucks, the platooning, we were trying to understand, compared to human drivers. The human drivers, we cannot really tell the drivers to stay even inside the same lane, where laterally the loading points are going to be. It's going to be a random distribution of load points laterally. The truck can be anywhere in the lane. But then with autonomous and connected trucks, we actually have a more precise control of where the lateral loading points are going to be. And then essentially our Dr. Accardi and his students worked on this together, and then to understand, under different different loading patterns and lateral displacements of the loading, under different schedules of the loading, and under different the frequency of the loading, essentially how close by each trucks are, how compact the truck convoy is. Then they have actually developed models to understand, again, finite element models to understand how the loading of the trucks in a platoon is going to have an impact on the payment damage accumulation over time and over space. So essentially, this helps us to understand the the damage to the payment. And then our colleagues also, Hassan Ozer, has also been particularly focusing. This is also research we have done in the past year or so regarding how as trucks gets closer to each other and travel at a higher speed, essentially the loading frequency gets improved, and then that's actually improved, but actually for payment is actually damaged, because the payment no longer have the time as a viscoelastic material to relax, to recover from the load. And then actually this more frequent loading from platoon trucks is essentially going to actually cause faster damage to the payment, and then there's reduced recovery time, and then essentially so they have done both modeling as well as done experiments to try to understand the impacts of those. And then finally, my colleague Jeff Ressler, I think he made a presentation earlier more about this work, so I'm only going to have 2 slides here to talk about what he did. He has been particularly focusing on how we can build new types of payments, and then actually embedding instruments inside the payment so as to help the platooning. So essentially that the infrastructure can communicate with a vehicle as they pass by. So this is just to show a little bit what he's doing. He put the magnetic electronic signatures in the payment so that actually the vehicles, when they pass by, they can have some certain guidance. And then particularly his work in the lab really gave us some ideas. I'm going to mention in a moment, that gave us some ideas about how, if we were to construct and convert the existing payments lanes into a a truck platoon capable ones, and how much is the cost of conversion. So we get data from them through this work. Okay, so with all this work of my colleagues, and then as you see, what we were trying to do is actually we have a complete, hopefully, understanding of the payment deterioration as they are under truck platoon. And any truck loading pattern configuration, we're able to understand how the progression of distress development, and essentially then how payment actually is going to deteriorate. And then we have this deterioration function. Then we will be able to put this actually next into a payment management model. In a sense, actually we can understand how we must be doing maintenance in order to maintain the state of good repair of the payment facilities. And at this together, we understand that actually the payment condition and the air drag. Remember, the fuel consumption has impact on the user cost. So just talking about all these things together, we're able to put all these components together into this payment lifecycle cost and actually system-wide lifecycle cost assessment framework. We are able to understand essentially how the platooning with or without platooning, then how much is actually really the life cycle cost implication of what we do. So what we do here now, so far we have been talking about the review of a previous work. Some of these slides have been covered in the previous year, but now in the past few months and then almost a year, what we were doing is that we are trying to put all these pieces together with our better understanding of the energy efficiency and better understanding of the payment impacts. We're trying to put together and see how we really can utilize all this information we obtained from our team's research to try to develop and plan the infrastructure or the network for line haul shipments, and then particularly to accommodate truck platooning. So this work is what we are doing is particularly trying to build sort of a network design model here to try to see where in an interstate highway network how we can actually build dedicated truck platoons. I'll talk about why we dedicate truck platoon in a moment, but generally, this is the type of infrastructure that actually the platooning benefits could be maximized. Anyway, we'll see that in a moment. So with all the research that we have been reviewing earlier with the work from our payment colleagues and then regarding error drag and so on. So we were thinking about actually how the system is going to work in the future with truck platooning capabilities. What we are trying to think is actually we would like to in the future allow a certain highway link to be sort of essentially converted into a truck platoon sort of a capable, right? Essentially, and then we were thinking about how we can actually, for any given traffic flow sort of pattern, how we can actually find out the best way to do the truck platooning, such that actually we minimize the overall cost, the life cycle cost regarding the energy consumption and the infrastructure impact. So what we're thinking first is actually maybe the public agency is going to come up with this sort of a truck platoon configuration, where that periodically the highway agency is going to actually look at the condition of the network regarding the demand and regarding the payment condition and so on. Then they will actually come up with the plan regarding a certain roadway link, how the link is going to be operated, and then what type of a platoon configuration is going to be. And meanwhile, then the agency is going to actually do payment management, essentially regarding the rehabilitation and then repair of the payment as traffic becomes intense. So the current setup is the following. So every certain period of time, we were tentatively thinking about 6 months of time, the public agency is going to try to come up with a way that, essentially the guideline or directive for the freight industry, where, if the freight carriers wants to use the platooning technology, and then it's almost like paying a toll, then essentially they would need to follow a certain configuration. So essentially the configuration is like a public directive, like controlled, in a sense. Actually the trucks are going to form a platoon of a certain lateral displacement, a certain clearance, and actually they will form platoons of a certain size. And here I want to explain a little bit here that what do I mean by the platoon size. Essentially, as we remember from the earlier research, the trucks actually forming a complete sort of alignment, then it's actually beneficial for certain benefits. Essentially, it will actually reduce the fuel consumption. But then if we have such concentrated load in this one, very much longitudinally aligned traffic, then the payment's going to get damaged very quickly. So what we were trying to do here is actually we came up with this scheme or strategy where the trucks form this type of platoons, small platoons, each platoon with a certain number N of trucks in it. This N is to be optimized in a moment, but then that's sort of the setup. So we form like convoys, multiple. Imagine that, if we have a platoonable lane, the traffic in it is going to be formed into multiple platoons or convoys, and each with N trucks in it. And then every platoon to another platoon, they are going to actually have a certain lateral displacement. So we can partition the lane, whatever lane we build for the truck traffic, then into multiple sort of a discrete sort of a displacements, and then the truck essentially just form a cyclic pattern as they travel. So one platoon is here, another platoon goes there, and then they rotates. In a sense, actually, they I don't know if this is clear. Essentially, we're going to have one platoon going like this, another platoon go like this, another platoon go like that. Essentially, they just do a cyclic type of then we come back to this side, and then we do this again. So this is sort of our sort of assumed track platoon operation plan. So and then this operation allows the payment to have a rest period in a way. So we have a platoon that's adding load to this area, and then the next platoon is go somewhere else, and then let this payment here to rest a little bit. This is essentially a strategy we propose here. Then this strategy, the whole platoon we call this platoon configuration, is going to be described by the lateral displacement, the clearance. Clearance is essentially the distance between the tracks, sort of the absolute clearance in between, and then the platoon size. And then we use the theta vector to indicate that. And then so this is, we assume this type of a control of the platoon is like a directive to the industry. Say, if you want to use this lane to do platooning, and then in this period of time, you follow this guideline. Somehow we find a way to organize the traffic through the control. Yeah? So this is one part of it. And then this platoon configuration could change over time. So every period of time, we can actually change it. And essentially this becomes, I call it, if we consider this in a sort of a long period of time in the life cycle of a payment, then essentially this becomes the platoon configuration schedule. So essentially you can imagine the platoon configuration could also change from 6 months to another 6 months because payment has been damaged a little bit more. Maybe we should change the platoon configuration and so on and so forth. So we consider this as something we can change over time, over a life cycle of a payment. Meanwhile, this is sort of how the traffic loading is going to be controlled. Another part is actually how the payment rehabilitation needs to be done over time in the life cycle of the payment. So the payment, particularly rehabilitation, when do we need to go repair the payments? So in Chicago, they do it every 2-3 years near the yards, the intermodal yards, but maybe other places every 10 years, other places every 20 years. So essentially some of these things are to be determined. So overall, these are the decisions we can make every 6 months or so regarding how we're going to run the traffic, how we're going to control the deterioration of the payment and then repair it. So with this, then we put this into this our sort of understanding of the payment damage propagation and energy, of course, as part of it. We assume that actually every payment facility, every roadway link is going to be running under a certain a traffic load and a platoon configuration. For any of those which we're going to optimize, we will be having the components from our earlier work from my colleagues regarding the payment 2D wonder. Essentially, this is the model that actually my colleagues in payment have developed regarding understanding under a certain truck loading pattern, how the payment is going to deteriorate over time. And then we also understand from my work, my colleagues, essentially how resurfacing and reconstructing some of the payments is going to have an impact on the payment and how much the cost is going to be. And essentially, in terms of a payment management point of view, we actually are continuously dealing with the impacts of the user cost. The user cost has to do with essentially the payment is getting worse and worse. And then there's cost associated with several parts. The vehicle wear and tear, that's actually the vehicle is gonna, the users actually has to pay extra vehicle wear and tear if the road gets rough. And there's also energy consumption we have talked about earlier regarding the air drag under a certain platoon consideration. And then there's also delay cost, of course, then when there's a lot of concentration of vehicles inside the lanes. And then the agency has to pay the rehabilitation cost of the payment. So essentially the decision every year, every 6 months, the agency has to decide what type of truck platoon configuration to use and what rehabilitation schedule to use. So this is essentially the problem we have. And then this problem is actually not that difficult. It turns out to be a simple optimization problem where we try to minimize the life cycle cost of the system actually in the lifespan of a facility, and then this includes the cost associated with the wear and tear, with the payment rehabilitation, and with the energy consumption, and all the things that we have talked about earlier. We can put them in this big framework, and then we have some there are some. I'm not going to bore you with the details of the math, but then essentially really just have all these models that are coming from my payment colleagues who have developed actually their models. For those of you who are on payments, they have the mechanistic empirical payment design guide, and then they modified it so in order to allow us to understand how payment is going to deteriorate under certain loading pattern and certain everything that we do. So essentially, with all these black boxes that we have in our colleagues' work, then we were able to put them together into this framework and then allow the decision making regarding platoon control, regarding payment rehabilitation. So with all those boxes ready, the problem actually itself is quite simple. It's, as those of you who are familiar with this is generally a dynamic program type. You can see we have a time horizon, we have multiple decisions, we have some schedule to optimize, and then essentially this is, I'm not going to bore you with the details. Essentially, we can define the stage decision epoch to be the every 6 months or every 3 months if you want, and then the state can be the payment state, and the action would be the platoon configuration and the payment rehabilitation decisions, sort of jointly optimized. And then the problem becomes a fairly straightforward Bellman equation. Then we can actually define the value function and then rewrite the optimization problem to be a stage-wise one. So that's what we did. Actually, it's very simple. We were just we were actually really integrating every component together in here. With this, what we did is that we actually were able to really here, we are just actually trying to understand what is really all the cost implied here. When we have a certain roadway link that actually is running a certain truck traffic, then how much is going to be the cost per vehicle, in a sense, or per user. And then, so now the interesting part, there are several things. We are able to actually apply the dynamic programming framework for every AADT, every sort of the traffic flow representation. Under that traffic flow, we optimize the lifespan of a sort of a loading pattern and so on. We're doing planning model, obviously. Then we try to come up with actually for every load, sort of a traffic volume, then we try to do the best platooning configuration, and then we are doing the best rehabilitation of the payments. Then we get to the cost of the per traveler here as a function of ADT. This actually, for those of you who are network modelers, this is actually, we were trying to mimic the BPR function in a way. The BPR function tells us actually when the traffic volume increases, what is the cost per traveler over essentially, you give me a traffic volume and what is actually the cost per traveler in there. And so this is actually, this chart here shows just, we were trying to mimic that, but we did a few things more. We are not just considering the delay anymore. Remember, we are considering mainly the energy and also the payment impact, the life cycle cost. So it's sort of what we call generalized link cost function. And then also interestingly, this link cost function is quite interesting. I want to point out that here, there's part about the agency cost, essentially how the agency is paying the rehabilitation of the payment. And there's some cost associated with actually users paying for the wear and tear. And roughness essentially regarding the wear and tear, when the payment gets worse, the vehicle depreciates faster. And then essentially, finally, the air drag cost regarding the energy consumption as we operate in such a condition. And then essentially, this is actually the optimized cost for every traveler if they were traveling at a certain traffic load onto a road link. Then essentially, something interesting here I want to mention. One is actually this curve, in contrast to the well-known BPR function, is that BPR function, normally we assume that actually the traffic, as traffic increases, the cost per traveler is increasing as a convex function. This is typically assumed, there's you can talk about fundamental diagram, and essentially there's other branches and so on, but essentially this is typically assumed in the literature. But with truck platooning, it's quite interesting. What we found is actually the cost function per truck, per traveler, whatever, unit cost, is actually a concave function typically. This is actually probably not surprising to you. I don't know if you ever thought about it with the platooning in traffic. So it's no longer like, say, the having one extra truck in the traffic, you are going to have sort of really bad impact on the congestion. You're going to, have everybody sort of clogged up. No, actually it turned out that actually having more trucks in the traffic, you may actually help other trucks reduce the energy. So you may be able to actually help a little bit in terms of the overall energy consumption, because there's a certain sort of a platoon effect where you have more traffic, you have fewer gaps, and then essentially the cost gets reduced. So there's some interesting effect there. And also in terms of delay for platoon trucks, there's another implication, I think, that we have because of the autonomous trucks, the trucks do not necessarily have to slow down when the flow increases. So that regarding the delay, the cost doesn't really increase as fast as you may actually anticipate with human drivers. So this is something that we found quite interesting here. So another thing that we found also just interesting and we need to note is actually with truck platoon, the capacity of the truck platoon lane is that we can actually come up with a formula for it. So essentially, for any sort of a spacing and a truck platoon size and so on, we can actually derive how many trucks can be accommodated if they were traveling at a certain speed, and then in a certain platoon configuration, we can figure out how many trucks can be accommodated by the truck lane per unit hour, let's say. Then essentially the capacity measure, the maximum flow we allow. So essentially you can imagine this function. We used to have a function that looks like this, and then this is a capacity. Now we have another capacity, and then but the concave function, and all of a sudden there's a jump here, sort of a discrete jump where the cost goes to infinity if this maximum truck flow allowed is exceeded. So essentially that's really where when the truck capacity gets the truck platoon actually gets, you cannot squeeze more trucks inside anymore. So I hope this makes sense. Essentially, we are trying to quantify this type of sort of the platoon cost on the links. And then also the final comment I want to make here is that actually the truck platooning, these costs, we put them all together here, assuming that actually the agency would have the control regarding how the platoons are going to be formed. But then some of the costs are borne by the agency as rehabilitation. Some of the costs are borne by the users. And then for truck platooning, there is a sort of an imbalance between the benefit and the cost as compared to human drivers. Human drivers, you pay, the carriers and the shippers, they pay the fuel, they pay the wear and tear of their vehicles, but then they rarely pay for the, the damage to the pavement. And I know that actually most of the states have a sort of a heavy vehicle fee for essentially, that's essentially the mechanism that the agency tries to let the users pay for part of the agency rehabilitation cost. I think that's actually important here, because otherwise, with truck platooning, all the benefits are borne by the users. They get energy reduction, they get smoother traffic and so on and so forth. But then the agency pays all the rehabilitation cost, the damage, right? So essentially, we think that actually this is something that we need to introduce a sort of a pricing scheme here to try to redistribute benefit and cost. And finally, I want to say that actually this comment here is actually whatever we are trying to show here as sort of the link cost function can only be achieved. This can only be achieved in a dedicated truck platoon lanes. If we allow mixed traffic, we allow mixed truck with the passenger cars, we think that's actually not efficient. Again, some sort of a hierarchy would be efficient, we believe, because you mix the trucks with the private cars and so on and so forth. The aerodynamics benefit wouldn't be as strong because of the different size of the vehicles. The air drag would, the benefit wouldn't come because you have two trucks and the 5 passenger cars in between. Essentially, no platoon is actually formed from an energy consumption point of view. And then so we believe that actually the energy benefit would be maximized under dedicated truck lanes. And also another thing is actually the traffic flow can be maximized under the dedicated truck lanes, and also for safety implications, we believe it's probably better to have dedicated truck lanes. So what we're going to do next is that we're going to be trying to look at how we can design dedicated truck lanes to try to maximize the benefit that we can get from truck platooning. So what we do here is we are going to be looking at a network design model next with the understanding of the link cost function, the new link cost function we characterized with all those components. We're now looking at actually how we can design or plan the next generation of our truck platoon lanes in the freeway network. So essentially, we are looking at where to locate dedicated truck platoon lanes, and essentially also how to redistribute the benefit and the cost, and what type of user fee we need to use to try to have a sort of a win-win situation. So we understand that actually whatever decision the agency makes regarding the truck platoon infrastructures would have an impact on the traffic in the transportation network. And then this will interact with the general public, as we said. So, and then we also want to mention that actually the autonomous trucks, the shippers can choose not to use platooning, right? They can still drive the trucks as they wish, as with human drivers. But we provide this opportunity to let them do the platooning in the network, and now this will interact with the traffic. then we understand all this truck traffic is going to have an impact on the pavement deterioration, and then this all those cost components that I already discussed earlier. Then all this is going to have a feedback loop on the traffic and on the freight efficiency. So this obviously have a lot of impacts on the economy, on the sustainability, and also on the durability of our infrastructures. And then this, particularly with truck platooning, is a significant problem. So we build a network design model. It's pretty straightforward network design model. So I will only quickly talk about the concept. Is that actually suppose that we're considering a problem that actually the state DOT probably, or maybe the feds would be interested in knowing, is that we have a transportation network, that's operating right now, in a state. Then the question is actually we have the freight traffic that's given to us. We need to serve them. Then currently we also have the public transportation demand that's actually also sharing the transportation network. Then the decision that actually we have is actually where do we actually potentially could try to add platoon lanes to the transportation network, such that actually we give an extra option for the truck traffic to try to get out of the mixed traffic and actually do platooning. And then essentially this I want to mention that this last layer of this network is essentially, it could be new additions of the lanes, or it could be conversion of the existing lanes. So then where do we do that? And then essentially we also want to understand how free traffic should be routed, how the public is essentially, I'm going a little bit fast here, but essentially how the traffic should be routed when we provide that, and then the public transportation should be provided, should be using the network. And then finally, we also simultaneously consider the payment rehabilitation plan, so that how to maintain the sort of the state of good repair in the network. So again, this slide I will skip. I think it's just a standard. Those of you who are familiar with network design, this is a standard bi-level model with agency decision at the upper level, and then the user decision regarding whether to use, the routing, and then the carriers and the shippers decide which route to use, whether to platoon or not on every link when there's an option. So just a quick showing of examples. We actually do have the Illinois example as a test case here. This is a Illinois sort of a freeway network, almost like here. And then we know the network topology, current infrastructure, and then we have the traffic, and then we have payment design information everywhere. Then we put all the components we discussed earlier about payment and traffic and so on together, and we were able to apply the network design model here to try to inform decision makers about actually, where, given the cost, given the budget, where we should actually be implementing truck platoon lanes. And then we will also be able to use our model to do sensitivity analysis, for example, to see, if we actually the cost of actually constructing or converting the lanes actually increases or decreases in the future, then how would the different costs change? I hope this makes sense. Essentially, that if the cost on the right hand side here, if the cost of conversion or platoon lanes is prohibitive, essentially nobody is gonna, the agency is not gonna put any platoonable lanes, no platoon traffic whatsoever. If that is the case, we have some breakdown of the costs here. Then if the conversion of the platoon lane is free, like there's no cost, we convert every parts of the roadway network potentially as an option for the users. And actually the difference here is actually the potential improvements we have from allowing platoons. And then this can be, then you can actually really, for agencies, you can look at, what is my, the cost of converting the lanes. You will be able to get the breakdown of the costs. But then if you really compare the cost of this left-hand side and the right-hand side, you will see that actually, here I have a little bit of a summary here, is that actually sort of interesting insights is actually when we don't do any platoon, platooning and so on, then essentially the air drag is really higher as compared to the when you do platoons. But then you will see that actually, but then the payment cost actually does increase a little bit, moderately, slightly, because the platooning does have an impact on. But with systematic coordination and a systematic design, we will still be able to save cost overall by about 20% for this particular case. Of course, every state is going to be different, and then situation will change. So this just gives us a little bit confidence. Actually, the potential work here could be used to save long-term life cycle cost for such systems. Okay, I think So I was thinking maybe I will touch on questions at the end, if that's okay. I know there's a question showing in the chat box, if I may, Debbie. Okay, I'll come back to your question, Dr. Hu. So a little bit, I'll go really quickly here. Another part of the work, we have actually been working on this for a couple of years, or 3-4 years now, actually, through various sources, but also we were happy to integrate this with our sort of a CCAT sort of a effort, is actually how we understand the impact of the last mile delivery by drones and how that's going to have an impact on the freight delivery system here. So just really quickly, I think since my time is limited now, I will just mention that actually the freight delivery, last mile delivery by drones is actually becoming a reality, maybe. It's actually happening. Amazon has been testing it for years, and actually almost every freight carrier is testing some sort of technology in this direction. And actually it turned out quite, it may be surprising to some of you, for short distance deliveries, using drones could be cheaper than other means. This is actually, again, for short distances, within 10 miles of a delivery, 5-pound package. Then Amazon drone, their target is $1 per delivery cost. Then this is actually considerably cheaper, really relatively, than if you were to drive a big truck or a delivery van and route around the neighborhoods to do the delivery. So this essentially is actually some interesting results we have. But with all this, and also another benefit of drone delivery is actually now we utilize 3D space, right? Rather than surface transportation, we now actually can utilize air. We can go across rivers fairly easily. We don't have to be limited by the geographical barriers and so on. But then drones also, UAVs also have shortcomings. And then one of the shortcomings is about particularly regarding energy efficiency. So essentially it does get big batteries and then you cannot carry heavy loads. So the Amazon only tested the 5 pounds. Anything heavier than that might be a problem or might be a challenge. And then there's limited flying heights and range. And then so the space actually, even though we go from surface to 3D, but then the flexibility that we have is also limited. And in particular, as in the future, as you imagine that the drone delivery becomes really the commercial level or the full scale, there are going to be a lot of drones flying around. In the neighborhood, there will be some concerns, at least regarding the congestion in the air. So we have been building, there has been different type of studies regarding how we should actually use, I will skip through this, different companies are trying drone, and Amazon is trying using the floating warehouses to try to, this warehouse flying on top of the air of a city, and then drones gets dispatched. The benefit of this is actually the drones is the freight is actually loaded to a certain elevation through certain this floating warehouse, and then it's more energy efficient. And then with a payload, the drone only go down, and then this probably will be costly and energy more efficient. And then when the drone tries to come back, it's empty. So this sort of a type of idea, Amazon actually patented this idea, is to try to potentially sort of overcome partially the shortcoming of UAV-based deliveries. All these things have been tested. But then what we are trying to do is really trying to understand what is the optimum sort of a layout if we were to cover a city last mile. And so imagine that we have trucks or Amazon floating warehouses going around the city, and then how the drones should be dispatched, and then how we should actually figure out the exact way to cover the whole city. So this is all of the research questions we were trying to address here. And then a little bit about the model, because now actually interestingly, the drones now travel instead of traveling in a lane, the drones travel in a continuous space. So we build more, I'm not going to bore you with the math, but we build continuous traffic equilibrium models where essentially we allow the drones to be flying like you can imagine water. Okay, they just flow in the continuous space, and then we try to figure out a way to figure out, each drone tries to find the optimal way to travel around. And then there is a congestion effect. If too many drones concentrate in a neighborhood, they slow down. So we actually do allow sort of a concentration to be imposing congestion to the drone traffic. So with this, we were able to I'll skip all the details. Essentially, the drone traffic is now actually the KKT condition for the user equilibrium, for example, can be described in equivalent form in the sort of PDEs, partial differential equations. So we have models to describe that. And then with this, I'll skip this. And essentially, we were able to study if we were to do last mile delivery from fixed sort of depots, or maybe from trucks that are actually ground based, then essentially how, how we can do that. And essentially some of the traffic patterns and how, essentially the traffic, you probably cannot see very well the arrows showing the path, the optimal path, because essentially there's concentration, and then the drones no longer travel in straight lines. They actually try to avoid each other and then try to travel around to avoid each other. We also consider the Amazon fulfillment center, the airborne warehouses, and then essentially we build models where, floating warehouses, and then the traffic, the destination is on the ground, then how the traffic is going to be routed. As you can see, some of the drones has to go higher than the floating warehouse just to avoid congestion in the bottom part of the airspace. So we have models to understand all these things. And then just a little bit for those of you who are interested in math, but just mention that we have the PDE formulation, we come up with the domain, we come up with a finite element mesh, and then we have all these elements members, and then we actually will be able to solve the PDE and find the travel path in as a vector field. It's just like how water is going to flow in the continuous space, and then that's optimum for every individual drone. With this, we are able to actually test, for Amazon or for any company, the last mile delivery, and how, if the city has different, for example, these barriers, we mimic the buildings near the urban setting, and then different values, and then we will be able to evaluate exactly what is going to be the congestion, the cost, and then the efficiency associated with the different settings of the city, and then we exactly knows how the drones needs to go from everywhere to everywhere in order to minimize the cost and energy and so on. Then we will be able to extract that information with some understanding of how the drone energy consumption is going to be related to the time, essentially the power, when they are doing different maneuvers. So if the drone is empty, they are actually going up, ascending, descending, or hovering around, or moving, horizontally. We have some numbers about the drone energy efficiency, and with a payload, the efficiency, and so on and so forth. Then we will be able to estimate based on the traffic we got from here. We know exactly the exact movement. We would be able to do line integrals in a sense, right? Each of this part we can map to some sort of drone movements here. Then we will be able to estimate the energy consumption for the drones exactly along the path. With this, we will be able to estimate the efficiency overall. So I hope this makes sense. And essentially, we were able to do different type of energy analysis, different scenarios. But eventually, what we do is actually we will be able to even to play around a little bit and under different design of the system. For example, I'll use this example, is that the Amazon might be curious about if they were to use the floating warehouses, airborne fulfillment centers, how high this floating warehouse should be above the air, right? Then essentially, then we notice actually as if they fly too high, energy consumption could be bad, because as you can imagine, there's less congestion, but then there will be a lot of free flow travel time in a way that actually the drones are overcoming too much distance. Or otherwise, if the floating warehouse is too low, there's huge congestion in the near ground space. So either way, we find there's certain, again, this data is not to advise Amazon quite yet, but just to give an example, there's a certain amount, location that the airborne fulfillment center, the height, then they should follow in order to minimize overall efficiency. And actually, there's also a comparison between the AFC versus ground-based travel. Remember, again, the AFC has already the load going up, sort of loaded up in the air. And then so there's energy savings. We are able to evaluate how much is a saving by the AFC, how promising it is as compared to ground-based delivery. So this is all the sort of some of the implications we could actually draw for the decision makers. Last slide, I think. With all this work, then where am I going? We are actually currently also considering the not only the freight. This is the last slide I want to say that our consortium here, our Illinois colleagues has been mostly focusing on freight deliveries, but we also want to mention even for the UAV, sort of air flying cars has been actually tested around the world, including Uber. And then maybe in the future, our work would contribute not only to the freight, but also to the passengers. And in the future, maybe you will not be actually limited by the surface roads and lanes and so on. You will be just actually flying all over the place. So our model would actually be hopefully be helpful in that regard. So with this, I think I conclude my presentation, and thank you very much for your attention.
Thanks, Dr. Ouyang. Why don't we go to the question from Dr. Hu? Can you briefly touch base on the state of the practice of autonomous truck implementation and testing? Are we getting close to seeing the fully autonomous trucks on the road?
I see. Thank you, Debbie. Thank you, Dr. Hu. I think that's a interesting question. Your actually, I think, since you asked that question, your answer is probably as good as mine in a way, because let me say that we have been following the we have been following the news as much, and we have been in contact with the industry. There are a lot of tests being conducted in the field, in Arizona, in different places, and so on. We think it's actually coming, and actually, honestly, I think maybe freight and actually heavy vehicle automation, that's my personal opinion, actually may actually happen earlier than the passenger vehicle transportation because of the, all kinds of reasons, the difference in the payload, so that's my personal guess. So I think it's probably coming. It will be sooner than the passenger side of things, in my opinion, freight side. So we are sort of in anticipation for its arrival, but I apologize. I cannot tell you a timeline because I'm not an expert on that. But I think it's coming, and it will be probably the first part of implementation. I think.
I know we're out of time, but I had one question too, and it was a follow-up to Dr. Hu's question, and that's there's a difference between what you're proposing and just a normal platoon. And so do you think to get the work that you do implemented, is it going to take like policy changes, for fleet, platooning in general, or do you think that just the fleet owner operators are going to implement it?
That's an excellent question, I think. I do think that there has to be a policy agreement. So the agency and the legislature needs to have this guideline so that actually the industry will follow it, because there's always going to be a chicken and egg issue, particularly when it has to do with infrastructure conversion and so on. And also, particularly as we mentioned, our analysis was focusing on sort of the life cycle cost of multiple sides, right? Like we have the infrastructure impact that's currently borne by the agencies, and then we have the benefit mostly borne by the users, and then there has to be a certain, just like pricing, we need to have this sort of policy instruments to actually to have a to create a win-win situation. And our sort of the promise of the promising view that we generate from this work is that actually we do have this opportunity to make the pie, I should say, bigger or smaller, I don't know, essentially that we have an opportunity to improve the overall system. Then the next is how we are going to distribute that benefit, and essentially between the different parties and the stakeholders. So that's actually the next step of the research, hopefully. So thank you, Debbie. I hope I answered your question.
Yeah, there's one more question from the audience. I figure we'll just do this one and be good. This is from Jay Lynn. Does your dedicated truck lane allow different classes/sizes of trucks to platoon? By doing so, do you anticipate reduced benefits or vice versa?
Yes, Jen, thank you for the question. I think right now we just consider one type of trucks. It's an exploratory study. We haven't considered multiple type of trucks, but from a nutshell, I think the benefit from air drag, particularly, that's a major source of sort of savings, would be maximized if we have similar trucks. Essentially, again, when the trucks are similar and then they line up, that's where the benefit comes the most, because the air drag gets reduced the most. But then if you have vehicle heterogeneity in the vehicles, then the air drag saving is limited by the smaller of the vehicle, in a sense, right? Whatever, you take the smaller of the two. So essentially we found like the benefit would be bigger to have the small conform trucks. We haven't studied at all. This is just recent work. We haven't studied that if we have mixed types of trucks. But I do think that actually differentiating the trucks from the from the passenger vehicles will be beneficial. So we sort of advocate for the dedicated lanes because it's for safety, for energy consumption, all those things. If you really mix up traffic, 2 trucks, 5 vehicles, passenger cars in the middle, essentially your platoon doesn't really save too much of energy for the trucks. So so anyway, just a preliminary thinking. So so thank you.